Hi, I'm going to explain the IEEE Paper of Deadline-constrained workflow scheduling algorithms for infrastructure as a service clouds. So let's begin with a very basic question. What is big data? Big data is the data we use every day through social media, public transport, GPS to store all this data, and to process all this data we don't need lots of big computers. Rather than we can use cloud computing to analyze the large number of data in minutes. So let's see what is cloud computing. To know what is cloud computing, we will take an example. Suppose a company needs a big ideas to stream all their business and drive their sales to roof. And to get this, they need a business apps, and business apps are too expensive. For this, they also need a team of experts to stock all the apps. So this will be too expensive to stock all the apps and to get business apps. To make this more cost effective, the company will use cloud computing instead of running all the apps themselves, and they will use shared data standards. For this, they just need to plug in the utilities, and it's faster and it's costless. Therefore, to run a business, companies don't need servers and storage, technical teams to handle all the apps. No software upgradations are needed. This all is done through cloud computing. Also, cloud computing is more scalable, more reliable, and more secure. So, what is the first step in cloud computing? First step in cloud computing is work scheduling. Before that, we will see that why we require cloud computing. On-demand resource provision is provided by cloud computing. Cloud computing provides a homogeneous network, and it provides a model of pay as you go. We will have to pay only for the resources we will use. So now come to the first step. What is the workflow scheduling in cloud computing? Workflow scheduling in cloud computing, as I said, that cloud computing is a set of large networks resources which are distributed over the network, shared among its users. A service by any user can produce a large amount of data, that is, he has to pay for the amount of the data he has used. So in this case, the data transfer cost between two dependent resources will be very high. Also, the complex application can have large number of tasks, which may cause an increase in total cost of the execution of the application if not scheduled in an optimized way. So, cloud computing aimed at the complete execution of the workflow by considering quality of service requirements such as deadline, budget, and deadline constraint and budget constraint. So now what is deadline constraint? Deadline constraint is a target data that indicates the task has to be completed on the particular time. In this paper, we will discuss about three algorithms of workflow scheduling, which will be PCP, ICPCP, and ICPCP-D2. PCP is used in grid computing. ICPCP and ICPCP-D2 are used in cloud computing. So let's see what is grid computing. Grid computing is composed of many loosely coupled networks acting together to perform the particular task. Now you may be wondering what is the difference between grid computing and cloud computing. So the difference between grid computing and cloud computing, let's take an example. For instead of taking hard drive for storage and the CPU for computation, the cloud computing takes some services to provide these resources to complete a particular task. So cloud computing uses resources to complete the task, but grid computing uses the network of computers to complete the task. So now what's PCP algorithm? PCP is used to minimize the cost of workflow while meeting the deadline defined by the user. This is PCP. PCP stands for partial critical path. And now we will see ICPCP and ICPCP-D2. ICPCP stands for IaaS Cloud Partial Critical Path, and ICPCP-D2 stands for IaaS Computing Partial Critical Path deadline distribution constraint. These two algorithms are used to handle large workflows because they both have polynomial time complexity. Let's move on to know what is IaaS. IaaS stands for Infrastructure as a Service. It is an instant infrastructure provided and managed over the internet. It quickly scales up and scales down with the demand as we pay only for what we use. Therefore, IaaS helps you to avoid the expense and complexity of buying and managing your own physical server and other data center infrastructure. Each resource is offered as a separate service component, and you only need to rent the particular one for as long as you use it. Let's move on to the next slide. There are two phases in PCP algorithm. So these two stages are deadline distribution and deadline planning. Now what is deadline distribution? It is the distribution of the overall deadline of the workflow across individual tasks. Planning is planning which schedules each task on the cheapest service that can execute the task before its sub-deadline. In this paper, what is the idea of PCP algorithm? So the idea behind PCP algorithm is combining and assigning a subroutine to each task and making a decision for scheduling each task together. Before beginning, let me tell you some abbreviations we have used in this paper. There are two nodes at the starting which we will make. Let me show you the diagram first and then it will be more clear. This is the diagram we are using for all the equations and all the three algorithms we are doing, and there are three algorithms and three equations we are using in this paper. So in this we are using 9 tasks: T1, T2, T3, T4, T5, T6, T7, T8 and T9, and we are added two nodes, T entry and T exit, to start and end the task. This will have 0 wait, T entry and T exit. So let me go back and tell you the full forms which we are using. T entry is a node without any parent node. T exit is a node without any child node. EST is earliest start time, EFT is earliest finish time, LFT is the latest finish time, MET is the maximum execution time, AST is the actual start time, TT is transfer time from one node, transfer of data from one node to another node. So as I told you, we are using 3 equations in this paper. Let's get started with the first one. So the first is EST of T entry will be 0. This is 0 because it has 0 wait, and we are not going to calculate any. It has 0 wait and 0 dependency and 0 execution, so T entry will be 0. In the beginning, weight of the nodes will be 0, calculating using fastest machine, as we are calculating this by using the fastest machine. So the first equation is EST TI will be equal to EST of a parent, TP stands for parent, plus minimum execution time for parent, plus data transfer time from parent, EP stands for parent and I for child. So it will be data transfer time from parent to child. TTEPI depends upon the assignment. TT will be 0 if parent and child are assigned to the same machine. So in this case, it will be constant. MET is used to calculate EST of the task which has not assigned yet. If it has assigned to the particular task on a particular service, then the execution time on that machine will be used. We will calculate maximum of EST, because when all the parent will be finished, we are able to calculate the earliest start time of the child. This is for equation 1. Now we are moving on to equation 2, is to calculate the EFT of the task, that is EST of the child plus MAT of the child. And these are also calculated using the fastest machine. So moving on to the third equation, LFT is of T exit is dead, no, is D, which is deadline. D stands for deadline. LFT is essentially the deadline because this is the latest a task can get started. If we will start the task later, then that will be miss the deadline. Okay. Now we can move on to the equation. This LFT or T1 is calculated to be minimum. So we are taking MAT, LFT of a child minus MAT of the child minus data transfer time from I to E. This is also calculated by using the fastest machine. If the task is assigned, TT will be 0. We have assigned any task, TT will be 0. We are taking this minimum because we are going to start TI as early as we can. We need to calculate what is latest time to execute TI. We will consider all child because each child is going to compose a constraint on the parent TI. Child cannot get started until all the parents are finished. Let's move on to the algorithm 1, which is ICPCP scheduling algorithm. And the second point, it is written, determine the available computation services. So this means that we are going to create a table such as, I will show you the table over here, table 1, which is the available computation services and their execution time for the workflow. So in this we have 3 services, means we have 3 virtual machines, S1, S2 and S3 over here. And we will decide for each task how long it's going to take for each virtual machine to be available. Virtual machine in this paper is allocated dynamically, and this algorithm is also using the dynamic virtual machine. So let's go back to the algorithm 1. Add T entry and T exit. These are the 2 nodes with the 0 execution time and 0 dependency, as I told you before. Now fourth point is to compute the EST, EFT and LFT using the fastest machine topology. Will be used and it will be from left to right in this algorithm. And the fifth one is we will calculate the actual start time. For the entry will be 0 and the actual start time for the exit will be D. Now when we all are calculated, that is EST, EFT and LST, we will mark T entry and T exist as assigned. And then we will move to the second algorithm, which will be the call assign parents over here. This algorithm is a bit interesting one. So this algorithm is going to call on the exit node, and this algorithm is a recursive algorithm. While loop identify over here, you can see the second point, identify all the unassigned parents. So in the diagram, T exit and has 3 unassigned parents. T exit has 3 unassigned parents, which are T7, T8 and T9. So while loop will have 3 iterations. Let's begin with the first iteration, T9. First, as an unassigned parent in beginning, partial critical path will be null for this. Then Ti is a current task, which is taken over here, Ti, right? So we have to calculate EFT of parent plus TT. It should be the maximum. Which parent data will be available at the latest? Because in order to execute the current task, we need to make sure parent is finished, but also the data is transferred. So let's see what will be the critical parent of T9. So T9 critical parent will be T6, as it is the only node. So now we will see the critical parent of T6. In this case, T6 has 2 parents, which is T2 and T3. Can you see? For this, we will, to know which will be the critical parent for T6, we will calculate the EFT of T3 and T2. Let's see the EFT from the table they have given in the paper. So in initial, the EFT of T3 and T2. Let's look at the EFT of T2 first. It is 5 and over here it is 3. Let's go back to the diagram. So if we it is 2 and it is 2. So if we plus EFT of T2 and T3, for T2 it is 5, so we'll plus 5 plus 2, which is equal to 7, and for T3 it is 3 plus 2, which will be equal to 5. So from this calculation we can see that T2 is a critical parent of T6. Now because it has EFT is equal to 7. You see that we have to calculate the maximum, as I told you. So in this case, T6 the critical parent of T6 will be T2. Okay. Now we will go to critical parent of T2, which is T entry over here, right? So we will not include that as it is already assigned. So partial critical path will be T2, T6 and T9, while loop will end over here. Now we will call assigned parent PCP, which means T2, T6 and T9 will go on the one machine. Idea of one machine, we need to make sure we can finish it before LFT of T9. So this will be move on to the algorithm 3, which is call assigned parents. Let me show you that over here. So it's saying in this algorithm it is saying that we have to use the cheapest path, path. So we cannot calculate LFT because LFT means latest finish time, as late as we can, but we are using the fastest machine. For this we have to use the slowest machine. So T2, T6 and T9 will run on the one machine, and we have to make sure that it can finish before the LFT of T9, right? So EST will become over here EST will become AST once the task is assigned. So we will take that as EST, right? So this algorithm can be used only when we are using the slowest machine, not the fastest one. Coming on to the 9th point over here. For all tasks T2, T3 and T9 will be updated and are successor of Ti. Successor here means those tasks which are not assigned yet. We don't have any in this case. In the 10th point, update LFT for all predecessors of Ti. So we will update LFT of T6, so we will modify the latest time of T3 to get better estimate of the deadline for T3, and this is calculated backward. Let me see the machine. So in this case they are using this virtual machine 2 from here. So in this case the weight of T6 is 8, as well as the weight of T9 is 8, and as well as the weight of T2 is 12. So LFT for T6, let's go back to the diagram, will be 30 minus 8, which will be 22, and T3 30 minus 8, we have calculated, right? Will be from here to here, this will be 22, and now for T3 it will be 22 minus 8, which will be 14, and we will minus this 2 also, which will, because it is using the other machine, it's running on the other machine, so we don't know which machine it is, but T2, T6 and T9 are running on the same machine, but not T3 is running on the same machine, it's running on some different machine. So we'll minus that, so the LFT will be for T3 will be 12. By this the first while loop ends, and we will go on to the second while loop, which identify the partial critical parent of T8, which will be, let's see, T5 and T4. Now we have to see on which virtual machine they are running on. They are running same on virtual machine S2. These machines, as I told you, are assigned dynamically in this paper. So T5 and T8 time. Let's see for the T5, it is 8, and for T8 this 6, right? So LFT of predecessor T5 has no predecessors. T8 has two predecessors, T4 and T1. Look, we had two predecessors. T4 and T1. So LFT will be, T8 will be taken 6 units. So LFT will be 30 minus 6, as we have seen. The T8 has a 6, and from that table, so this will be 24, but it's running on some other machine, so it will be 23. So LFT for T4 will be 23. So LFT for T1 now will be 23 minus 4, which is 19, but it's running on some other machine, so it will be 18. Now we will move on to the 12th point, which is called assigned parent will be a T8, because T5 have no critical parent. T8 has a critical parent T4, and T1 is a critical parent of T4. T1 and T3 are going to run on virtual machine S3. T1 is equal to 8 over here, and T4 is equal to 10 units. T1 and T4, there are no predecessor but one successor, which is T7. So LFT of T7 will be adjusted. EST of T1 will be 0. EST of T4 will be 8, because T1 takes 8 units. T7 for EST of T7 will be 10 plus 8, because T4 takes 9 units. And also we will plus 1 over here, because we are going forward. It will be 19. So EST for T7 will be 19. So this will end with the second while loop. And in third while loop, only which node is left now? T7. So in T7 PCP will be the critical path will be T7 only, as all the other paths are assigned. So let's see the critical pair. What will be the number LST of T7? So it is coming from T4 and then it's coming also taking T1, so it will be 10 plus 8. So LST is of T7 will be 8, as we have seen from the table earlier that the time of T1 and T2, because running in the same machine, these are running in the same machine, so we will not take 1 in this concentration. So now what is the time complexity by using all the algorithms? We see the complexity, overall time complexity of ICP-DP2 is O(n)2, O(n) square. Performance evaluation. In this, here we are taken some example of workflow to evaluate the performance of ICP-CP and ICP-CP-D2. There are some diagrams which are shown over here. They are taking some workflow diagrams. These are calculated by using two ways, which is DHE, that is by using graph, and one is by using the library of the workflow, realistic one. So in the experiment, they have taken 10 different services with the processor speed, which will be different, and it has different prices. The processor speed is chosen randomly. Model is assumed to be pay as you go, and the total cost is normalized. The assigned deadline to each parent, they have assigned deadline to each parent. So in this result, we can see that they have compared the three algorithms: ICP-CP, ICP-CP-D2, and IC loss. By using all these 5 structures, they have taken out the graph by calculating the deadline for each workflow, and we can see that ICP-CP has a better performance than ICP-CP-D2. The blue ones are ICP-CP, so you can see that they are the cheapest ones. So let me tell you what we have learned in this paper. In the beginning, we added the T entry and T exit node, then we calculated EST from left to right, and then we calculated LFT backward, and while calculating we use the fastest machine. T exit is called to see the assigned parent. Inside this we find the critical path and then assign all critical path on one machine. While assigning one machine, we use one exiting machine if possible without missing the deadline, and here the deadline is LFT of each machine, of each task. Predecessor of the task will be adjusted like we have done with the T3. Successor of the task will be adjusted like we have done with T7. Each task we will call their parent. This algorithm calling the assigned parent. This assigning the task to the resources and making the adjustment with the deadline and at the same time. So thank you.